Okay, hi everyone. Welcome back to my channel again. The last video I have discussed some of the basic information and then concepts which are important to learn or to know basic concepts of econometrics. But today I have decided to bring here or to present or discuss more topics which are thought to be the prerequisite concepts or topics to learn or succeed in the course econometrics. So also while we are discussing the basic concepts of econometrics last time, I have discussed that having a course in basic mathematical studies is a non-negotiable prerequisite for any serious course in econometrics. And I also told because of that for this that economics course have two objectives and we have to focus on this. So on one of its basic objective or first issue is that it is to show how various quantitative techniques can be used to fit models given a suitable data. And this is relatively easy. And the other is to develop an understanding of the statistical properties of these techniques and hence an understanding of why they work satisfactorily in certain contexts and not in others. I think this is much more demanding and it does require a good basic knowledge of statistical theory and mathematical statistics as well. So we can combine them and able to estimate or formulate a model which predicts or explains a certain phenomena of the real world. So this is what we have discussed last time. Today, I have tried to bring you some of the basic mathematical statistical tools that you can use so that we can able to learn the econometrics course more easily. Let's start. There are three parts in this review or mathematical statistics, and the first part which deals about random variables. The second one is we will try to look at the test statistical significance of given parameters, and also the last we'll look at probability concept and distribution as well. Let's start from the first topic, which is discrete random variable and expectation. So we also try some part of continuous random variables and expectation because we face both discrete and continuous random variables when we make or analyze econometric parameters. So here this will have random variable and expectation, variance, covariance, and correlation. This all the three concepts are really related. This one, the first one, random variable and expectations. This is what we are going to look today. Variance, covariance, and correlation. We'll look them in the next video. Sampling and estimators. So we'll look also the estimator for the populationist parameter, and then this is also case, and then we also check the unbiasedness, and we'll check whether the expected values of a sampling distribution of an estimator is equal to the unknown true value of the population parameter or not. So we'll check also efficiency here. So the minimum variance concept will be introduced in this case, and we'll check them as well as whether the parameters are efficient or inefficient. I mean, estimators are efficient or inefficient. And then we'll look at the normal distribution, sometimes what we call quotient distribution. And then this is one which follows a symmetric, or they are symmetric about the mean. That means the data which shows that the data which is near to the mean are more frequently in occurrence than that of which are far from the mean. So that appears it is a bell curve or when we crowd the data set. So we'll look also for this is also parametric data. We'll check later on. And then let's start today from the random variable and expectation. So when we come to random variable, will have different concepts about randomness. So sometimes we call them a stochastic variable, or they are called also random quantity. Random quantity. So it is a mathematical formalization of quantity or object, which depends on random event. So random experiment or event. So this is when we don't know the how or what will be occur. We know the possible outcomes, but we don't know 100%, or we are not sure or certain about the event to occur. So the term random variable in mathematics may also refer neither randomness or variable, because it is a mathematical function which tells that the domain is that of some possible outcomes that in the sample space. Example, tossing of a coin will have head and tail, which are the possible upper side or flip coins, and then that's head or tail, and then which are resulted from a sample experiment, that's tossing of a coin, or this range is measurable space. So we know what will be occur or what will be happen, but we don't know which one will be happen. So there are more than one events to occur. So the corresponding domain or the range may be the set of some given element. So let's say head and then tail. So typically the range of random variables is a set of a real number. So for our instance, for example here, we can pick an example that we can flip a one-sided coin and also flip a two-sided coin. So we'll expect different events or outcomes in this context, because when we flip one-sided coin, we 100% know that which event will occur. But when we flip two-sided coin, we are uncertain whether it's head or tail. That's the best example of what a random variable means. So we can more discuss example. For instance, in case of tossing of an unbiased coin. An unbiased coin means that the randomness of the tossing of the coin is not subject to some error or other issue. So if there are 3 tails, then the number of times head appears can be random variable, because there is another variable which has the probability to occur, that is tail. So this has the values maybe 0, 1, 2, or 3 for head. So since the 3 tails, we make it a minimum of 0 heads or a maximum of 3 heads. So the probability of a head to occur when you toss a coin is either 0 head or 1 head. When you toss again or flip again, it may be the same, and then this is how we express probability, random variable. So there is a certain probability concept which is involved when we discuss about a random variable. So it is an outcome of random experiment. So without random experiment, we may not have a random variable. So for example, we don't when we toss a coin, this is called random experiment, and then the outcome will be a random variable. So here it's a simple example, is picking card from a well-shuffled deck of cards. So well-shuffled means that we check whether it is subject to biasness. So so that we don't have any concern, or we don't have any information about the card we are going to draw. So both or all of 52 cards have the same probability, equal chance to be selected. This is why we say biasness will be minimized when they all have equal chance, and the randomness will be thought to be the case. And the other basic thing is that we use these random variables in econometrics or regression analysis so that we can determine statistical relationship between different variables. This is the use. And again, we classify random variables based on the probability distribution. So a random variable either has an associated probability distribution, that is for discrete random variable, or a probability density function, that is for a continuous random variable. Therefore, we have two types of random variables, which is discrete and continuous. So, when we talk about discrete random variables, they take only one countable number of distinct values. So, usually these variables are counted. They are not, so if a random variable can take only finite number of distinct value, then this variable is thought to be a discrete random variable. So, for instance, we can pick a total score when two dice are thrown, a number of members in a family, or number of defective, let's say, light bulbs in a box of 10 or 100 bulbs, and etc. are an example of what we call discrete random variable. So the probable distribution of this variable is the list of probabilities associated with each of its possible value. So it is what we call probability function, or sometimes it is equivalent with probability mass function. And then that's the case. So we'll determine more. And then when we come to continuous random variable, they are variables that take up an infinite number of possible values, which are usually in a given range. So it may be an age of a person, so from 0 to somewhere. And then typically these are measurements actually, like weight, height, that at a time which is needed, a time for some, a time need to finish some work, and so on. So we can give more example. For example, the life of an individual in a community is continuous variable or continuous random variable. Let's say that the average lifespan of an individual is 100 years. So therefore, a person can die immediately on the birth, that is where the life is equals 0 years, or after some years of an age which is 100 maximum. So within this range, he can die at any age. So therefore, a variable age can take any value from 0 to 100. So since continuous variable don't have specific value, then the number of values is infinite. Also, the probability at specific value is must be there. We don't have the probability specified. So instead, it is defined over a range or an interval of values, and then represented by an area under a curve. We'll look later sometimes. So here's we can measure at any specific time, and this is the case. We'll talk more about the probabilities of random variables of continuous with continuous character when we discuss later about the expected values of continuous random variable. So let us talk about the expected values of discrete random variables. We call sometimes it expectation, or it is population mean. So for population mean or random variables, and therefore it measures the center of distribution of a random variable. So the expected value of a random variable, let's say x, will be written as e the bracket x. So that's called expected value of random variable x. So sometimes we use a mean or something x, and then it is a long run mean in the sense that if as more and more values of random variable were collected by sampling or by repetition of probability activity, the sample mean becomes closer to the expected value. So for the discrete random variable, the expected value is calculated by summing. Here, as you look, by summing the product of values of the random variable and its associated probability. So taken overall the values of the random variable. So it is symbolized in this way. So we can easily calculate in this way. We'll have an example which is related with this one. Let's say consider a simpler example of random variable, the number we obtain when we throw just one die. So when we throw one die, we obtain there are six possible outcomes to our shot. So an example of the random that is not discrete is that it is a discrete random variable, and then it's not continuous because we count it. say 1, 2, 3, 4, 5, 6, and there is no interval in this score. So we will have an example, and when we probably toss a coin, we will have a die will have this possible outcomes, each with the same or each with equal chance to occur. So it's unbiased, it will have an equal chance to occur. Then it's possibly from as we have mentioned earlier in this course, in this slide, we defined that we can easily calculate the expected value or population mean for discrete random variable in this way. That is multiplying each possible values of random variable by its probability and summing up it. So the same thing is here. We have when we throw a dice one time, we'll have a possibility of 6 values or 6 outcomes to occur. So either 1, 2, 3, 4, 5, 6 occurs. So we can calculate the expected value in this way. So one has a chance to occur, so 1 over 6. Then in this way, everyone has the probability to occur, and the probability will be made in this way. So in short, it will be 3.5 when you do this simple calculation, and then it will be 21 over 6 or 3.5. So the total expected value will be this one. In the next video, we'll discuss about population mean, or what we call expected value of continuous random variable. This is for today. It's over. Thank you very much.